A spiral galaxy spins in perfect silence against the dark. But what if the universe is hiding structures so bizarre they defy our understanding of physics itself? We are about to journey through 25 of the most puzzling galactic structures ever discovered. By the end, you will have witnessed a tour of the universe's greatest architectural enigmas, from perfect cosmic rings to invisible walls billions of light-years long. We will see how a single galaxy can be a perfect circle, and why astronomers argue over a giant arc that should not exist. Which cosmic mystery do you think will challenge our reality the most? Our first stop on this tour of cosmic oddities is a galaxy that looks like a target floating in space. In 1950, astronomer Art Hogue was surveying the sky when he found something that made him pause. There, in the constellation Serpens, was a perfect ring of brilliant blue light encircling a golden core, with a dark, seemingly empty gap between them. It was so geometrically perfect he initially thought it might be a visual artifact, a trick of his telescope, but it was real. This is Hogue's object, a galaxy that defies the chaotic, swirling norm. The structure is breathtaking in its simplicity. At its heart lies a dense, spherical core of older, yellow stars, much like the central bulge of a typical spiral galaxy. But instead of spiral arms, a near-perfect circle of young, hot, blue stars surrounds it like a cosmic hula hoop. The most striking feature is the gap, a dark band of space that appears almost completely empty, cleanly separating the two stellar populations. It is this pristine division that makes Hogue's object so profoundly puzzling. How does a galaxy form with such perfect symmetry? The leading theory points to a violent past. Billions of years ago, a smaller galaxy might have plunged straight through the heart of a larger disk galaxy. The gravitational shockwave from that collision could have triggered a wave of star formation that rippled outward in a near-perfect circle, leaving the older core undisturbed. Another idea suggests it began as a barred spiral galaxy, where the central bar became unstable and dissolved, its stars migrating outward into that remarkable ring. Yet both explanations struggle to account for the ring's flawless circular shape and that mysteriously clean, dark gap. For now, Hogue's object remains a celestial masterpiece, a single, perfect question mark hanging in the void. Yet Hogue's object is a solitary wonder in deep space. Our own home galaxy harbors a colossal mystery, one invisible to the human eye but blazing in high-energy light. Emanating from the very heart of the Milky Way are two enormous lobes known as the Fermi bubbles. Picture two colossal balloons, each one a blistering hot structure of gamma rays and high-energy particles bulging outward from the galactic center. They stretch an astonishing 25,000 light-years upward and downward, meaning the entire structure is 50,000 light-years tall, half the diameter of the Milky Way's own spiral disk. We are living inside a galaxy that is, in a very real sense, blowing giant bubbles. These structures remained completely hidden until 2010, when scientists analyzing data from the Fermi Gamma Ray Space Telescope noticed an unexpected excess of gamma ray emission. It formed a distinct symmetrical shape, a figure 8 of intense energy centered on our galaxy's core. The discovery was a shock. For all our maps and surveys, we had missed a feature so vast it towers over everything else in our galactic neighborhood. The central puzzle is what created these titanic structures. The leading theory points to a cataclysmic event at the galaxy's core, where the supermassive black hole Sagittarius A star resides. Millions of years ago, this black hole may have experienced a violent feeding frenzy, devouring an immense amount of gas and dust. The energy released from this feast could have been channeled into two powerful jets, erupting perpendicular to the galactic plane and inflating these gigantic bubbles with ultra-fast particles and magnetic fields. An alternative theory suggests not a single explosive event, but a period of frenzied star formation in the crowded galactic center. If hundreds of massive stars were born and died in supernova explosions in quick succession, their combined stellar winds and shockwaves could have blown these bubbles outward over time. The bubbles themselves are not empty space. They are filled with a thin but incredibly hot plasma, a soup of charged particles moving at nearly the speed of light, all tangled within powerful magnetic fields. This magnetized plasma acts like a giant particle accelerator, slamming electrons around to produce the gamma rays we finally detected. So while they are invisible in ordinary light, these Fermi bubbles are a permanent, energetic monument to a dramatic chapter in our galaxy's history, a reminder that even our cosmic home has explosive secrets buried in its past. But the universe's grand architecture does not stop at our galactic doorstep. Stretching across an almost unimaginable portion of the cosmos is a discovery so vast it has astronomers questioning a foundational rule of the universe itself. This is the giant arc, a colossal crescent of galaxies, galaxy clusters, and intergalactic gas that spans an incredible 3.3 billion light-years. To grasp that scale, if you could hold a ruler to the sky, this structure would cover roughly 1/15 of the observable universe. Its discovery was announced in 2021 by doctoral student Alexia Lopez, who was analyzing the light from distant, brilliant quasars. As this light travels billions of years to reach us, it passes through the vast clouds of material between galaxies. Specific elements in these clouds, like magnesium, absorb very specific colors from the quasar's light, leaving dark lines in the spectrum like cosmic fingerprints. By mapping where these absorption lines appeared across the sky, Lopez noticed a startling pattern. Dozens of these clouds were not randomly scattered. They aligned along a gentle curve, tracing a structure of staggering proportions. The immediate and profound problem with the giant arc is that, according to a cornerstone of modern cosmology called the cosmological principle, it should not exist. This principle states that on the very largest scales, the universe should look roughly the same in every direction and be smooth without any dominant structures. There is a theoretical size limit, about 1.2 billion light-years, beyond which matter should be distributed evenly. The giant arc is nearly 3 times that limit. It is a statistical anomaly so extreme it is like rolling a dice and getting 100 sixes in a row. The discovery has ignited fierce debate. Some scientists argue it could be a fluke, a chance alignment of smaller structures that only appears connected from our particular vantage point in the cosmos. Others see it as a potential crack in our standard model, a hint that the universe might be more textured and lumpy on grand scales than we ever thought possible. If the giant arc is real and truly coherent, it forces a difficult question. What physical process in the early universe could have orchestrated matter across such an impossible breadth, weaving a pattern that defies our understanding of cosmic evolution? While the giant arc hints at a universe more crowded with structure than we imagined, other regions of the cosmos present the opposite problem, a profound and unsettling emptiness. Drifting through the constellation Bootes is a region so barren it has earned the nickname the Great Nothing. This is the Bootes Void, a spherical abyss of near-total darkness roughly 330 million light-years wide. To comprehend that scale, if you placed our Milky Way at one edge, you would need to travel for hundreds of millions of years at the speed of light through almost pure nothingness to reach the other side. In a universe teeming with billions of galaxies, this void is a staggering anomaly. A volume of space this immense should contain around 2,000 galaxies. Instead, astronomers have found only about 60, leaving a cosmic desert of incomprehensible proportions. The mystery is not just that it is empty, but how such a vast emptiness could form at all. The leading theory involves a process of cosmic consolidation. Think of the universe's large-scale structure as a vast cosmic web, with dense filaments of galaxies surrounding empty bubbles. The Bootes Void might be where several of these smaller bubbles merged over billions of years. they're walls of galaxies retreating and leaving behind one colossal, unified emptiness. It could be a fossil, a remnant of the universe's earliest, lumpy conditions that never filled in. Yet even within this great nothing, there are whispers of existence. Scattered like lonely islands in an endless ocean, a handful of isolated galaxies persist. One of the most famous is MCG plus 01-02-015, a spiral galaxy so isolated that if you were born on a planet there, your night sky would be almost devoid of other galaxies. These void galaxies are mysteries in themselves, having evolved in profound isolation, untouched by the gravitational dances and collisions that shape galaxies in denser regions. The Boots void, therefore, is not just an absence, it is a dominant feature of reality, a chilling reminder that the cosmos is not uniformly filled, and that our rich galactic neighborhood might be the exception rather than the rule in an infinite sea of nothing. Even within the vast emptiness of the Boots void, a handful of galaxies cling to existence, but to find the universe's true architecture, we must look at the walls. For years, the title of the largest known structure belonged to a titan of the cosmic web called the Sloan Great Wall. Discovered in 2003, this is not a solid barrier but a staggering filament, a dense river of superclusters, galaxy clusters, and thousands of individual galaxies, all gravitationally bound into a single meandering structure roughly 1.4 billion light-years long. To visualize that, if you could see it in the sky, it would stretch the length of over 1,400 Milky Ways placed end to end. Its discovery was made possible by one of the most ambitious maps of the cosmos ever undertaken, the Sloan Digital Sky Survey. Using a dedicated telescope, the project methodically scanned vast swaths of the heavens, recording the positions and distances of millions of galaxies. When scientists began plotting this three-dimensional map, a pattern emerged from the dots. Galaxies were not sprinkled randomly like salt. Instead, they clustered into immense sheets and long, thread-like filaments with enormous empty voids between them. The Sloan Great Wall was the most spectacular filament of them all, a backbone of the cosmic web. This structure perfectly illustrates the large-scale organization of the universe. Think of the cosmos as a sponge or a collection of soap bubbles. The glowing walls of the bubbles are these great filaments and sheets where galaxies congregate. The empty spaces inside the bubbles are voids like the one in Boots. Our own Milky Way resides within a smaller sheet of galaxies called the local sheet, which is itself part of the far larger Laniakea supercluster, a tributary flowing into the universal web. The Sloan Great Wall's immense size presented a serious puzzle for cosmologists. Structures in the universe grow from tiny, random fluctuations in density after the Big Bang, slowly pulling together under gravity over billions of years. Computer simulations of this process could produce walls and filaments, but a structure as colossal as the Sloan Great Wall seemed statistically very rare, perhaps too rare to find so relatively close to us in cosmic terms. Its existence suggested that the early universe might have had larger seeds, greater initial clumpiness than our best models predicted. It was a record-holding giant that challenged our understanding of how the cosmos builds itself, proving that the universe's largest patterns were even grander and more complex than we had dared to imagine. Yet even the staggering scale of the Sloan Great Wall was eventually overshadowed by a discovery so immense it seems to break the rules of the cosmos. This is the Hercules Corona Borealis Great Wall, a structure so vast it stretches an almost incomprehensible 10 billion light-years across. To put that in perspective, this single feature spans over a tenth of the entire observable universe. It is not a wall of bricks and mortar, but a colossal concentration of matter, a superstructure of galaxy clusters and superclusters woven together by gravity. The most astonishing part is how we found it. Astronomers did not see it directly by mapping galaxies. Instead, they charted the cosmic fireworks of gamma-ray bursts. These bursts are the most powerful explosions in the universe, thought to signal the death of massive stars or the collision of dense stellar remnants. The logic is brilliant. Where you find a high concentration of these catastrophic stellar deaths, you are likely looking at a region densely packed with galaxies and the massive, short-lived stars within them. By plotting the locations of hundreds of distant gamma-ray bursts, a pattern screamed from the data. They were not randomly scattered. They traced a rough, wall-like structure in the constellations of Hercules and Corona Borealis, a region of space so densely packed with stellar activity it defies belief. This discovery plunged cosmology into a deep and ongoing controversy. The Hercules Corona Borealis Great Wall appears to be roughly twice the size of the theoretical maximum for any cosmic structure, a limit derived from the cosmological principle. That principle, a bedrock of modern science, says the universe should be homogeneous and isotropic on the largest scales. It should not have features this dominant. The existence of this wall suggests the universe might be lumpy and textured on scales we never thought possible, like a tapestry with a pattern larger than the room it hangs in. Skeptics argue the wall could be a statistical illusion, a chance alignment of separate clusters that only looks connected from our particular viewpoint. Others have proposed even more exotic ideas, questioning whether our understanding of gamma-ray bursts is complete, or if some unknown, large-scale process in the early universe could have woven matter into such an impossible tapestry. For now, the Hercules Corona Borealis Great Wall stands as the ultimate challenger, a ghostly outline on our maps that asks a terrifyingly simple question. What if the universe is not as smooth as we think, and we are simply living in one of its smaller wrinkles? While the Hercules Corona Borealis Great Wall challenges our view of the universe on the grandest scales, a far more intimate and ghostly structure drifts right through our own galactic neighborhood. Arcing across the southern hemisphere's sky is a faint, shimmering ribbon of gas known as the Magellanic Stream. This colossal river of hydrogen stretches over 600,000 light-years, more than 6 times the diameter of our entire Milky Way galaxy. To the unaided eye, it is completely invisible, but through the ears of radio telescopes, it sings a faint song of its ancient and violent history. This stream is the torn and tattered tale of our galaxy's 2 largest satellite galaxies, the Large and Small Magellanic Clouds. For centuries, these 2 hazy patches of light have been familiar guides to southern sky watchers. But only in the 1970s did astronomers using sensitive radio antennas discover they were not alone. They were dragging an immense gaseous wake behind them. The leading theory for this stream's creation is a story of gravitational theft. As the Magellanic Clouds have orbited the Milky Way over billions of years, our galaxy's immense gravitational pull has been like a cosmic tide, relentlessly tugging at them. This tidal force is thought to have stretched and ripped vast clouds of gas from the smaller galaxies, flinging this material out into a long, arching trail that now encircles almost half the sky. It is a slow-motion act of piracy, with the Milky Way stripping raw material from its smaller companions. However, there is a competing and equally compelling explanation. Perhaps the stream was not pulled out by our galaxy, but blown out by the clouds themselves. Within the Magellanic Clouds, there are regions of intense star formation, where massive stars live fast, die young, and explode as supernova. These explosions, combined with the fierce stellar winds from giant stars, could have created powerful galactic winds, blowing huge amounts of gas out into intergalactic space. As the clouds moved, this expelled gas would have been swept back, forming the ribbon we see today. The true answer likely involves both processes, a complex dance of internal violence and external theft. But the story of the Magellanic Stream does not end with its creation. This vast reservoir of gas is not static, it is falling. Gravity is pulling the stream inexorably down toward the disk of the Milky Way. In the distant future, perhaps in 1 billion years or more, this primordial hydrogen fuel will finally rain down upon our galaxy's spiral arms. When it does, it could trigger a spectacular new wave of star formation, seeding nurseries for new suns and planets. So this faint, ghostly trail is more than just a cosmic curiosity. It is a pipeline of future creation, a river of potential returning to its galactic source, reminding us that even the quietest structures in the sky are chapters in an epic story of destruction and rebirth. While the Magellanic Stream is a river of potential falling toward us from outside, another cosmic projectile is hurtling toward the Milky Way from within our own territory. This is the Smith Cloud, a colossal, fast-moving island of hydrogen gas on a direct collision course with our galaxy's disk. Discovered in 1963 by astronomy student Gail Smith using a radio telescope at Leiden University, this cloud appeared as a strange, fuzzy patch of radio emission, a silent and massive specter drifting against the stellar background. But as measurements improved, its true nature became clear. This is no ordinary cloud. It is enormous, stretching over 11,000 light-years long and 2,500 light-years wide, containing enough gas to forge over 2 million suns like our own. And it is moving at a blistering speed of over 200 miles per second, aimed almost directly at the spiral arm we call home. The profound mystery of the Smith Cloud lies in its origin story. When astronomers analyzed its chemical composition using ultraviolet light from distant quasars shining through it, they found a critical clue. The cloud is rich in heavier elements like sulfur, which are forged in the hearts of stars and scattered by their explosive deaths. This signature suggests the cloud did not form in the pristine emptiness of intergalactic space. Instead, it was born in the star-rich environment of the Milky Way's outer disk. The leading theory paints a dramatic picture. Billions of years ago, some cataclysmic event, perhaps a cluster of supernova explosions or a close gravitational encounter with a smaller galaxy, violently ejected this massive blob of gas from our galaxy's outskirts. It was flung out into the galactic halo, the sparse spherical region surrounding the main disk, where it has been traveling on a vast, elliptical orbit for eons. Now, like a cosmic boomerang, it is coming back. In roughly 30 million years, the Smith Cloud will slam into the galactic plane. The impact will not be a single, explosive crash, but a prolonged and spectacular celestial collision. As the leading edge of the cloud plows into the denser gas of the Milky Way's disk, it will create immense shockwaves, compressing the gas in both the cloud and the galaxy. This compression is the primary trigger for star birth. The collision will likely ignite a brilliant firestorm of new star formation, a dazzling burst of stellar nurseries and brilliant young stars across a region thousands of light-years wide. It will be a localized but intense fireworks display on a galactic scale, a temporary blaze of blue light and radiation. For astronomers, the Smith Cloud is a rare and precious preview. It offers a front-row seat to the process of galactic accretion, the way galaxies like our own gather fresh material to fuel their future. We are witnessing a delivery of raw, star-making fuel, a process that was far more common in the chaotic early universe but has now slowed to a trickle. This imminent impact shows us that our galaxy is not a static island. It is a dynamic, ever-changing ecosystem, still gathering its building blocks from its own extended halo. The Smith Cloud is a messenger from our galaxy's past, returning to shape its future, reminding us that even the quietest spaces between the stars hold the momentum of cosmic events yet to come. The fate of the Smith Cloud is a future event written in gas, but the history of our galactic neighbor is written in stars. Encircling the great Andromeda galaxy is a faint, ghostly river of suns known as the giant stellar stream. This colossal structure is not a neat spiral arm or a glowing nebula. It is a sprawling, tangled ribbon of countless individual stars, stretching across hundreds of thousands of light-years and wrapping around Andromeda's majestic disk like the tattered remains of a cosmic battle. This stream is the archaeological evidence of a galactic cannibalism that occurred billions of years ago. Andromeda, like most large galaxies, grew to its immense size not just by forming its own stars but by consuming smaller neighbors. The stellar stream is the debris left behind from one such ancient feast, the torn-apart remains of a dwarf galaxy that ventured too close. As this smaller galaxy was drawn into Andromeda's overwhelming gravitational embrace, it was stretched and shredded over eons. Its stars were pulled out into long, looping orbits, creating this vast and diffuse river that now orbits the larger galaxy. It is a fossil record written in starlight, a direct snapshot of the violent process of galactic evolution. For astronomers, these streams are like celestial crime scenes. By meticulously mapping the positions, movements, and even the chemical compositions of the stars within the stream, they can attempt to reconstruct the original victim. They can ask, what kind of galaxy was this? Was it a small, faint dwarf spheroidal or something more substantial? When did this merger happen, and from what direction did the smaller galaxy approach? The answers are encoded in the complex distribution of stars, but decoding them is a monumental challenge. The stars from the devoured galaxy are now hopelessly mixed with Andromeda's native stars. Untangling this stellar DNA requires incredibly deep surveys and sophisticated computer simulations that model billions of years of gravitational interactions. It is a puzzle where the pieces are scattered across an immense volume of space, and the picture on the box has been lost to time. Each new observation of the stream adds a clue, helping to refine the story of this ancient collision, reminding us that the serene beauty of a spiral galaxy often masks a dramatic and violent history of conquest and assimilation. The serene halo of our galaxy holds more than just isolated stars. Hidden within the constellation Virgo lies a sprawling, ghostly structure known as the Virgo overdensity. This is not a bright nebula or a distinct cluster, but a vast and diffuse cloud of millions of stars, smeared across an area of sky nearly 5,000 times the size of a full moon. It was discovered not by seeing a glowing patch, but by counting. When astronomers sifted through the immense star catalogue from the Sloan Digital Sky Survey, they noticed a curious excess. In the direction of Virgo, there were simply more faint stars than anywhere else in the galactic halo. It was as if someone had taken a handful of stellar dust and sprinkled it thinly across a colossal volume of space. The sheer scale of this structure is bewildering. It spans at least 10,000 light-years, and its stars are intermingled with our own, making it a part of the Milky Way's extended halo, yet clearly distinct from the smooth background. The central mystery is what exactly this stellar cloud represents. One compelling theory is that we are witnessing a dwarf galaxy in its final death throes. A small satellite galaxy, perhaps only a fraction of the Milky Way's mass, ventured too close billions of years ago. Our galaxy's immense gravity has been slowly pulling it apart, stretching its stars into this immense, faint stream that we now see as the overdensity. It is a process of tidal disruption happening in ultra-slow motion. Another possibility is that this is the remnant of a massive globular cluster, a tightly bound family of stars that was somehow ripped open and scattered. Or perhaps it is something even more primordial, a rare fossil relic from the Milky Way's own chaotic construction phase, a clump of material that never fully collapsed into a recognizable shape. The clues are maddeningly subtle. The stars in the Virgo overdensity are old and metal-poor, meaning they formed early in the universe's history from mostly hydrogen and helium. This supports an ancient origin, but it does not distinguish between a cannibalized dwarf galaxy and a primordial cloud. Its very low density and immense spread make it incredibly difficult to map its full three-dimensional shape or trace the precise motions of its stars, which are the keys to unlocking its past. So this vast stellar haze remains an enigmatic signature in our own backyard, a silent reminder that the history of our galaxy is written not just in its brilliant spiral arms, but in these faint, ghostly ruins that linger at the edges of perception. Wrapping around our galaxy like a faint, celestial serpent is a structure that challenges our very map of home. The Monoceros ring is a vast, looping band of stars and hydrogen gas discovered in 2002 that appears to lie in the outer reaches of the Milky Way, stretching across the constellations Monoceros and Canis Major. From our vantage point inside the galaxy, it looks like a separate ring or stream encircling us, a giant hoop tilted against the main plane of the galactic disk. This immediately presented astronomers with a fundamental puzzle. Are we looking at the mangled remains of a small galaxy being consumed, or are we simply misreading a distorted part of our own? The first and most dramatic theory paints a picture of galactic cannibalism in progress. This ring, according to some researchers, is the tidal debris of a dwarf galaxy being torn apart by the Milky Way's gravity. The suspected victim is the Canis Major dwarf galaxy, considered by some to be the closest known galaxy to our own, though it is so thoroughly disrupted it is almost unrecognizable. In this scenario, as this dwarf galaxy made repeated close passes, our galaxy's tide stretched it into a long, looping stream of stars and gas that now orbits us, appearing as the Monoceros ring. The evidence comes from the types of stars found within it. Surveys have identified concentrations of specific, older stellar populations and certain types of variable stars that are common in dwarf galaxies, but less so in the Milky Way's thin outer disk, suggesting an external origin. The competing theory argues we are guilty of cosmic myopia. It suggests the Monoceros ring is not an invading structure at all, but an intrinsic part of the Milky Way we simply failed to understand. Our galaxy's disk, long pictured as a flat, thin pancake, is now known to warp and flare at its outer edges. Imagine taking a thin vinyl record and gently bending its outer rim upward on one side and downward on the other. That warp, combined with a thickening or flaring of the disk's edge, could create the illusion of a separate ring when viewed from within. In this view, the stars of the Monoceros ring are simply the outermost citizens of our own galaxy, born in situ and following orbits that take them far above and below the galactic plane. The debate is far from settled, and it hinges on forensic astronomy. To determine the ring's true origin, scientists need precise measurements of two key pieces of evidence. First, the motions of its stars. If the ring is tidal debris from an accreted dwarf galaxy, the stars should share a distinct, coherent motion, a signature of their shared origin as a single system that was disrupted. If it is the warped outer disk, the stellar motions will be more varied, following the expected patterns of galactic rotation, albeit on exaggerated orbits. Second, their chemical composition. Stars born together in a small dwarf galaxy tend to have a similar and typically metal-poor chemical fingerprint. Stars born in the Milky Way's outer disk might show a different signature. New data from missions like the Gaia spacecraft, which is mapping the positions and motions of over 1 billion stars with unprecedented accuracy, is providing these crucial clues. Early analyses are complex, with some studies supporting the accretion model and others favoring the warp model, keeping the mystery alive. So this faint ring of light is more than a curiosity. It is a test of our ability to read our own home's architecture. Is the Milky Way a neat, flat spiral with a few digested companions, or is it a more complex, three-dimensional structure whose outer boundaries are twisted and flared in ways we are only beginning to see? The answer will tell us not just about this one ring, but about the very shape and violent history of the galaxy we call home. The debate over the Monoceros ring asks what shape our home truly takes, but an even more profound question emerges. What if our entire galactic neighborhood is not just warped but floating inside a cosmic void? This startling possibility is the core of the KBC void hypothesis, named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie. Their work suggests we are not in an average region of space. Instead, our Milky Way sits near the center of an immense spherical bubble of nothingness, a local underdensity roughly 2 billion light-years across. Think of the universe's large-scale structure as a vast sponge. Most galaxies cling to the dense, luminous walls of the cosmic web. According to this idea, we are not on a wall. We are in the hollow center of one of the sponge's largest bubbles. The evidence comes from counting. When astronomers survey the galaxies around us, they find fewer of them than standard cosmological models predict for a random spot in the universe. Measurements of distant supernova used as cosmic mile markers also seem to indicate that space in our local volume is expanding slightly faster than the global average. This is a critical clue. In an underdense region, there is less gravitational pull from surrounding matter to slow down the expansion. So galaxies on the edge of our local bubble would appear to be fleeing from us a bit more quickly. If the KBC void is real, it solves one major puzzle while creating another. For years, astronomers have been troubled by a discrepancy called the Hubble tension. This is a growing conflict between two ways of measuring how fast the universe is expanding, known as the Hubble constant. Measurements based on the early universe's afterglow, the cosmic microwave background, give one value. Measurements using nearby supernova and other local markers consistently give a higher, faster value. The existence of a giant local void could explain this discrepancy perfectly. Our local, faster expansion rate would not represent the true, global speed of the cosmos. It would be a local illusion, a product of our unusual address in a vast emptiness. Our telescopes would be biased, like a weather station placed in a desert, incorrectly reporting the planet's overall humidity. The controversy is fierce. Many cosmologists argue that a void this large is statistically extremely unlikely in our standard model of the universe. They suggest the galaxy count data could have other explanations, or that the methods for measuring distances locally might have subtle, unaccounted for errors. To settle the debate, we need deeper and wider galaxy surveys, mapping the cosmic web in 3 dimensions around us with unprecedented precision. The implications are staggering. If we are inside the KBC void, it means our most fundamental measurements of cosmic expansion, and therefore our calculations for the amount and influence of dark energy, might need a significant correction. Our entire view of the universe's fate could be skewed by the quiet emptiness of our own cosmic backyard. It is a humbling thought. The greatest mystery in cosmology, the nature of the universe's accelerating expansion, might be intertwined with the simple, haunting question of where, in the grand scheme of things, we actually live. Even our place in a possible cosmic void cannot explain a motion that seems to defy the very fabric of reality. Across the observable universe, entire clusters of galaxies are streaming in a single, coherent direction, as if caught in a river flowing toward an unseen shore. This phenomenon is called the dark flow, and it is one of the most contentious discoveries in modern cosmology. The story begins not with visible light, but with the oldest light in existence, the cosmic microwave background. This faint, cold glow is the cooled remnant of the Big Bang's fireball, bathing the entire universe in a nearly uniform radiation. It is the ultimate backdrop, the still canvas upon which the universe paints its structures. In the 2000s, a team led by astronomer Alexander Kashlinsky studied this background with unprecedented precision using data from the Wilkinson Microwave Anisotropy Probe satellite. They were looking for a specific, subtle signature. As massive galaxy clusters move through space, the hot, thin gas trapped within their gravitational grip interacts with the cosmic microwave background photons in a predictable way. This interaction, known as the kinematic Sunyaev-Zeldovich effect, creates a tiny, telltale temperature shift in the microwave background in the direction of the cluster's motion. It is like seeing the wake of a ship on a calm sea, revealing its direction of travel. When Kashlinski's team analyzed hundreds of distant clusters, they expected to find these motions were random, canceling each other out as the universe expands uniformly in all directions. Instead, they found something shocking. The clusters, scattered across billions of light-years, appeared to be moving together in a coordinated stream toward a single point in the constellations Centaurus and Hydra. This coherent motion was not just a local fluke, it extended to the very limits of the data, suggesting a flow on a scale that should be impossible. The speed was staggering, estimated at hundreds of miles per second. The implication was profound and unsettling. For such a vast, coordinated motion to exist, it must be caused by a gravitational pull of unimaginable strength, a pull coming from something so massive it lies beyond the edge of everything we can see. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang, roughly 93 billion light-years across. The dark flow suggests that something enormous, far outside this sphere, is tugging on the matter within our visible cosmos. This is where the debate reaches its peak and theories venture into the extraordinary. One radical explanation points to the multiverse. In some models of cosmic inflation, our universe is one bubble in a frothing sea of eternally inflating space-time. Other bubble universes could exist beyond our observational horizon. If one of these neighboring universes passed extremely close to ours in the higher dimensional bulk of reality, its immense gravitational influence could, in theory, reach into our bubble and pull on our galaxy clusters, creating the dark flow. It would be evidence, however indirect, of a cosmos vastly larger and stranger than our own. Skeptics offer more conventional explanations. They argue the signal could be an artifact of incomplete data or a systematic error in how the cosmic microwave background is measured and interpreted. Perhaps our maps of the microwave background are not yet precise enough, or our understanding of the physics within galaxy clusters is incomplete, leading to a false pattern. Subsequent studies have yielded conflicting results, some supporting the original finding and others finding no evidence for a large-scale flow, keeping the controversy fiercely alive. The dark flow, therefore, is more than a mysterious motion. It is a direct challenge to our cosmological horizon. It asks if the universe we see is truly all there is, or if we are merely a small part of a structure so grand its true shape lies forever in shadow, its gravity reaching in to guide the motion of galaxies like unseen hands in the dark. The dark flow hints at forces beyond our sight, but some of the universe's largest structures are visible yet no less mysterious. Drifting through the primordial darkness of the early cosmos are colossal, amorphous clouds known as Lyman alpha blobs. These are not galaxies, but something more primal and immense. Each blob is a gigantic, nebulous cloud of hydrogen gas, one of the largest single objects in the universe, spanning hundreds of thousands of light-years across. To hold one in your mind, picture a cosmic jellyfish, a diffuse and glowing mass of gas so vast it could swallow our entire Milky Way and its neighboring galaxies with room to spare. They are found only in the distant, early universe, their light traveling for over 10 billion years to reach us, making them snapshots of a time when the cosmos was in its turbulent youth. The name comes from their eerie glow, a specific wavelength of ultraviolet light emitted when electrons within hydrogen atoms drop to a lower energy state. This Lyman alpha radiation paints these titanic clouds in a haunting, monochromatic light, visible only to our most powerful telescopes tuned to see the distant universe. The central, burning puzzle is what makes them shine so brightly. A cloud of hydrogen gas left to itself does not simply light up. Something must be pumping tremendous energy into it, causing it to fluoresce like a cosmic neon sign. The first theory points to a frenzy of creation happening inside the blob itself. These could be nurseries on a staggering scale where thousands of galaxies are being born at once. Within the cloud, pockets of gas collapse to form stars at a ferocious, unprecedented rate. The combined ultraviolet blaze from billions of newborn, massive stars would then ionize the surrounding hydrogen, causing the entire colossal structure to glow in that characteristic Lyman alpha light. It would be a single, glowing incubator for an entire future cluster of galaxies. A second theory looks to a more violent engine. Perhaps at the heart of each blob lies a supermassive black hole in its most active quasar phase. As vast amounts of matter spiral into the black hole's accretion disk, it heats to incredible temperatures, blasting out intense radiation across the spectrum. This torrent of energy from the central beast could be illuminating the entire surrounding gas cloud from within, like a lighthouse bulb embedded in a globe of fog. A third, more subtle idea suggests the glow is not from heating but from cooling. In this scenario, the blob is a massive halo of dark matter, pulling in vast rivers of primordial gas from the cosmic web. As this gas flows into the halo, it collides and shocks, radiating away its gravitational energy as heat, which is then emitted as Lyman alpha light. The blob glows because it is settling down like a hot piece of metal cooling and giving off a visible shimmer. They are, in essence, cosmic embryos. Each Lyman alpha blob may be the precursor to the most massive structures we see today, like the great walls and superclusters of galaxies. We are witnessing the raw material of the cosmic web aglow with its own latent energy, a fleeting stage in the universe's construction where the blueprints of future grandeur are first illuminated. They are ghosts of the young cosmos, showing us the moment when the universe began to gather its matter into the architecture we now call home. While Lyman alpha blobs glow from the depths of cosmic time, a structure of comparable scale was hiding much closer to home, concealed behind the brilliant veil of our own galaxy. This is the South Pole Wall, a colossal filament of the cosmic web stretching a staggering 1.4 billion light-years across the southern celestial hemisphere. For all our surveys of the distant universe, this immense wall of galaxies remained one of the last great uncharted territories in our own cosmic backyard, simply because we were looking right through it. The problem is called the zone of avoidance. From our vantage point within the Milky Way's spiral disk, the dense band of stars, gas, and dust that forms the plane of our galaxy creates a thick, obscuring fog. It is like trying to see the landscape beyond a mountain range while standing in a dense forest at its base. For centuries, this zone blocked our view of nearly 20% of the extragalactic sky, creating a giant blind spot in our map of the local universe. The South Pole Wall lay directly behind this curtain. To unveil it, astronomers could not rely on traditional optical telescopes. Instead, they turned to a clever workaround using the cosmic fingerprint of redshift. As galaxies move away from us due to the expansion of the universe, their light is stretched to longer, redder wavelengths. By meticulously measuring this redshift for hundreds of thousands of galaxies using dedicated surveys, scientists can calculate not just their direction but their distance. It is a form of cosmic echolocation, using light instead of sound to build a three-dimensional map. In 2020, a team led by cosmographer Daniel Pommard did exactly this, compiling redshift data from multiple surveys and applying sophisticated computer algorithms to filter out the foreground clutter of the Milky Way. What emerged from the data was a breathtaking revelation. Looming behind the southern galactic plane was a vast, dense concentration of galaxies, a sweeping wall-like structure that rivals the famed Sloan Great Wall in scale. It arcs across the constellations, from the southern celestial pole toward the constellation Cetus, forming a backbone of the local cosmic web. Its discovery fundamentally reshapes our understanding of local cosmic geography. We now see that our own Laniakea supercluster, the vast continent of galaxies that includes the Milky Way, is not floating in isolated grandeur. It is likely a mere appendage, a spur, or an outlying region attached to this far more massive South Pole Wall. This wall is a gravitational watershed, a continental divide on a cosmic scale, where the flow of galaxies is directed by its immense mass. mapping such a nearby titan is not just an exercise in cartography. It is crucial for calibrating our cosmic rulers by providing a precise, local measurement of how matter is clustered on the largest scales. The South Pole Wall helps astronomers refine their models of both the universe's expansion rate and the distribution of the invisible scaffolding of dark matter. The wall's immense gravity subtly influences the motions of galaxies for hundreds of millions of light-years around it. By studying these motions, scientists can weigh the structure, inferring how much dark matter is woven into its fabric alongside the visible galaxies. So this newly revealed wall is more than a hidden neighbor. It is a fundamental reference point, a colossal signpost that helps us measure the dynamics and contents of the entire local universe, proving that some of the most important discoveries are not always at the edge of the observable cosmos, but sometimes hidden in plain sight, waiting for us to look in the right way. The hidden architecture of our galaxy runs even deeper than the Fermi bubbles. From the same violent heart, astronomers have now mapped a pair of colossal, faint chimneys, vast conduits of energy that might be the very foundations of those giant bubbles themselves. These structures are known as the galactic geysers, and they reveal an eruption of truly staggering power. Their discovery came not from gamma rays but from radio waves using the exquisitely sensitive Mercator telescope in South Africa. While mapping the turbulent region around the galactic center, Mercator's data revealed two towering columns of magnetized, energetic particles, each one reaching for about 500 light-years above and below the galactic plane. They are not solid pillars, but rather vast, diffuse funnels like the base of two immense hourglasses placed back to back. The most compelling detail is their location. These radio chimneys align perfectly with the center of the Fermi bubbles, appearing to connect the supermassive black hole's immediate neighborhood directly to the base of those gargantuan lobes 50,000 light-years tall. This suggests we are not looking at separate features but parts of a single, integrated system. The geysers could be the fossilized channels, the ancient pathways through which the energy from the galactic center was transported outward to inflate the bubbles. Imagine a volcano. The Fermi bubbles are the vast plume of ash and gas that has spread across the stratosphere. The galactic geysers are the volcanic vent itself, the throat through which all that material first erupted. This connection points to a cataclysm far more focused and energetic than we had imagined. The event that created these structures, whether a black hole feeding frenzy or a starburst episode, did not just release a diffuse cloud of energy. It focused that energy into two powerful, collimated jets or winds that punched directly upward and downward through the galaxy's dense central region, clearing out these immense chimneys before spreading out to form the bubbles. This makes the original eruption even more impressive, as it had to overcome the immense pressure and density of gas in the inner galaxy to establish these clear pathways. Furthermore, the geysers might be part of a vital galactic feedback loop. As energy and hot gas surge up through these chimneys, they eventually rain back down onto the galactic disk in distant regions. This process can regulate star formation, heating up gas clouds to prevent them from collapsing into new stars too quickly, or conversely, triggering new star formation when the falling material collides with the disk. The geysers, therefore, are not just relics. They might be active components in our galaxy's circulatory system, a way for the central engine to influence its entire domain, proving that even a quiet black hole today can sit within the echoing infrastructure of its own past fury. Yet even the colossal chimneys of our galaxy's center are dwarfed by a structure of perfect geometry far beyond our own. Drifting in the constellation Leo, nearly 1 billion light-years away, is a celestial arrangement so precise it seems almost artificial. This is the ring of galaxies in Leo, a near-perfect circle of 9 distinct galaxies, each one a brilliant island of billions of stars, all tracing a cosmic circle over 300 million light-years across. Its discovery was a quiet revelation, emerging not from a single dramatic image, but from the patient analysis of vast galaxy survey data. Astronomers mapping the three-dimensional distribution of the cosmos noticed this peculiar alignment, a statistically improbable ring where none should exist. The puzzle is profound. Gravity, over billions of years, tends to create clusters and filaments, not perfect circles. A ring this symmetrical, maintained across such an immense scale, defies our expectations of how cosmic structures naturally evolve. The leading explanation, however, reaches back to the very birth of the universe, to a time before stars or galaxies even existed. This ring may be a colossal fossil, an imprint of sound waves echoing through the newborn cosmos. In the first 380,000 years after the Big Bang, the universe was a searing, opaque plasma, a dense soup of particles and light. Within this primordial fluid, pressure waves rippled outward from any slight overdensity, like sound waves moving through air. These were true acoustic oscillations, compressions and rarefactions racing through the hot plasma. Then, in a flash, the universe cooled enough for atoms to form, allowing light to travel freely in what we call the cosmic microwave background. That sudden transition froze these sound waves in place, imprinting a preferred scale into the distribution of matter, a scale of about 500 million light-years. This frozen ripple is known as a Barrian acoustic oscillation. It acts like a standard ruler etched into the fabric of space, a subtle ring-like pattern that influenced where galaxies would later form. The ring of galaxies in Leo may be one of the clearest, rarest examples of this phenomenon made visible. We are not seeing a structure that formed recently from gravity. Instead, we are seeing the ghostly outline of a pressure wave from the universe's first moments, a pattern in the primordial plasma that guided these 9 galaxies to coalesce along its ancient crest, like dew collecting along the rim of a spiderweb. It is a direct snapshot of the universe's infant cries, preserved for 1 billion years in the arrangement of celestial giants. Our galaxy is held together by a ghost. The most massive component of the Milky Way is not its brilliant spiral of stars, nor its vast clouds of gas. It is an immense, invisible sphere of dark matter, a halo of unknown substance that envelops our entire visible galaxy like an ethereal cocoon. This dark matter halo is estimated to be over 10 times more massive than all the ordinary matter we can see, and it stretches for nearly 1 million light-years from the galactic center, far beyond the outermost visible stars. We cannot see it, touch it, or photograph it, yet we know it is there because of its gravitational grip. The very fact that our galaxy does not fly apart reveals its presence. Stars on the outer edges of the Milky Way's disk orbit the center at speeds that defy the pull of visible matter alone. According to the laws of gravity, with only the stars and gas we see, these distant stars should be moving much more slowly. The fact that they whip around so quickly means there must be an enormous amount of unseen mass holding them in place, a dark anchor woven through and around our galaxy. We map this phantom halo by watching how things move within its influence. The orbits of distant stars, the paths of globular clusters, and even the trajectories of small satellite galaxies like the Magellanic Clouds all act as tracers. By measuring their speeds and positions with extreme precision, astronomers can essentially perform a cosmic weigh-in, calculating the distribution and amount of the invisible mass that must be tugging on them. It is like deadening the shape of a fan by watching the swirl of leaves caught in its breeze. The profound and unsettling mystery, of course, is what this dark matter actually is. For decades, the leading candidate has been a hypothetical particle, something slow-moving and massive that interacts only through gravity and perhaps the weak nuclear force. These WIMP, or weakly interacting massive particles, would form the cold, invisible scaffold upon which galaxies like ours are built. Yet the halo itself presents puzzles that challenge this elegant picture. Computer simulations of cosmic evolution based on the cold dark matter model predict very specific structures for these halos. They suggest the density of dark matter should spike sharply toward the galactic center, forming a steep cusp. However, observations of the actual motions of stars and gas in the inner regions of our Milky Way and other galaxies suggest a gentler, flatter core. This is the core cusp problem, a persistent mismatch between what our theories predict and what we seem to see. Another glaring issue is the missing satellites problem. Those same sophisticated simulations show that a galaxy the size of the Milky Way should be surrounded by thousands of small dark matter clumps, each one potentially hosting a tiny dwarf galaxy. Yet we have only found about 60 such satellite galaxies. Where are the rest? Have they simply not formed stars, remaining utterly dark? Or is there something about the nature of dark matter or the complex physics of star formation in tiny halos that we do not yet understand? These are not minor discrepancies. They are fundamental tensions that force us to question our most basic assumptions. Is dark matter a simple, cold particle after all? Or could it be something more complex, perhaps even interacting with itself in ways that smooth out those predicted cusps and suppresses small clumps? The invisible architecture of our galaxy, therefore, is not just a solved mystery. It is an active crime scene where the gravitational clues left behind by stars are pointing toward a truth about the universe that remains, for now, shrouded in profound and beautiful darkness. The invisible halo of dark matter sculpts our galaxy's outer reaches, but the inner dynamics are shaped by a visible yet enigmatic backbone. At the very heart of the Milky Way, spanning an immense 27,000 light-years, lies a dense, rigid structure of ancient stars known as the galactic bar. This is not a feature we can see with our own eyes, for it is buried behind thick veils of interstellar dust in the constellation Sagittarius. Our solar system actually orbits within one of the spiral arms that emanate from this bar's ends, placing us in the galactic suburbs with a profoundly obscured view of downtown. For centuries, astronomers inferred the bar's existence indirectly by studying the motions and distributions of stars that seem to follow a rigid, elongated pattern rather than a perfect circular orbit around the center. But confirmation required looking with new eyes that could see through the dust. That breakthrough came with infrared astronomy. Infrared light, with its longer wavelengths, slips through the obscuring dust clouds that block visible light. Space telescopes like the Spitzer Space Telescope and ground-based surveys meticulously mapped the heat signatures of millions of stars, revealing the bar's stark outline for the first time. Radio telescopes added another layer, tracing the distribution of cold hydrogen gas that also aligns with this central bar. The combined picture was undeniable. Our galaxy is not a simple, elegant spiral. It is a barred spiral, its central bulge stretched into a rigid, rotating candy bar of stars. This bar is not a static ornament. It is a dynamic engine, a great gravitational stirrer that profoundly influences the life of the galaxy. As the bar rotates, its immense gravitational field acts like a cosmic plow, pushing and pulling on the vast clouds of gas and dust that drift through the inner galaxy. It funnels this raw material inward along lanes called dust lanes, channeling it directly toward the crowded galactic center. This process serves a dual purpose. First, it supplies fuel for intense bursts of star formation in the central molecular zone, a region brimming with turbulent gas. Second, it delivers a steady trickle of gas all the way to the doorstep of the supermassive black hole, Sagittarius, a star, potentially regulating its activity over eons. The bar's very existence and its slow, steady rotation solve one mystery while creating another. How did this structure form in the first place? The leading theory involves a gravitational instability. In the early Milky Way, the central disk of stars may have been unstable to a specific kind of disturbance, like a ripple in a pond. Over time, the collective gravity of the stars themselves amplified this ripple, causing orbits to align into an elongated shape that eventually locked into place as a rigid, rotating bar. It is a self-organizing structure born from chaos, yet the bar's life is not static. Simulations suggest that bars can evolve, even dissolve and reform over billions of years. As the bar rotates, it can transfer angular momentum to the surrounding dark matter halo, causing the bar itself to slow down and potentially thicken. Some models even suggest that a very massive central concentration of mass, like our galaxy's black hole, could eventually destroy the bar, causing it to buckle and morph into a more spherical bulge. So the galactic bar we see today may be a temporary phase in our galaxy's long evolution, a central engine currently driving its growth and activity, but destined to change its shape in the deep future. We are living in the age of the bar, a period where the backbone of our galaxy actively shapes its own destiny. Our galaxy's grand bar stirs the inner depths, but our own stellar neighborhood is shaped by a much closer and more intimate structure. Just a few hundred light-years away, we are embedded within a colossal, tilted ring of young, brilliant stars and stellar nurseries known as the Good Belt. This is not a distant curiosity. It is our local cosmic district, a sprawling disk of star formation about 3,000 light-years across, tilted roughly 20 degrees to the main plane of the Milky Way. Within this belt lie many of the night sky's most famous jewels. The mighty Orion Nebula, a stellar maternity ward, is part of it. So are the bright stars of the Scorpius-Centaurus Association, including Antares, and many of the brilliant blue stars in the constellations of Perseus and Lupus. We are essentially living inside a local spur or a giant, expanding bubble within the larger Orion arm of our galaxy, a region buzzing with recent stellar birth. The Good Belt's origin is a classic cosmic whodunit. How did this vast, tilted ring of young stars and gas come to be right here, and why is it angled against the galaxy's main disk? The prime suspect is a titanic explosion from the distant past. Imagine a massive star, many times heavier than our Sun, reaching the end of its life millions of years ago somewhere near our present location. Its catastrophic supernova death would have blasted a shockwave of unimaginable power through the surrounding interstellar clouds. This shockwave, expanding like a fiery plow, could have compressed vast tracts of gas, triggering a chain reaction of star formation that propagated outward in a ring, creating the Good Belt we see today. In this scenario, we are witnessing the aftermath of a single, local cosmic detonation that reshaped our galactic neighborhood. Yet another compelling theory points not to a sudden bang, but to a slow gravitational sway. The Milky Way's disk is not perfectly rigid. It can oscillate, warp, and ripple over vast scales due to interactions with satellite galaxies or the inherent lumpiness of the dark matter halo. A large-scale gravitational instability, a kind of slow-motion wave passing through the galactic plane, could have gathered and compressed gas over a wide area, initiating the widespread star formation that defines the belt. This would make the Good Belt a local expression of the galaxy's broader dynamics, a ripple in the pond where we happen to float. Its proximity is a gift to astronomy. Because the Good Belt is in our backyard, we can study the entire life cycle of stars with unparalleled clarity. We can observe dense molecular clouds before they collapse, witness the violent birth of stars within nebulae like Orion, and track the dispersal of young stellar clusters as they drift apart. It is a grand, nearby laboratory for understanding how star formation propagates through a region, how stellar winds and supernova from one generation of stars can trigger the birth of the next. This local ring, therefore, is more than just a beautiful arrangement in our sky. It is a dynamic chapter in the ongoing story of our spiral arm, a clue to the forces that sculpt the galaxy on the scale of our own experience, reminding us that even our familiar night sky is part of a vast and evolving structure. But even the grandest structures can be torn apart by a single, catastrophic event. In the constellation Ophiuchus, nearly 400 million light-years away, astronomers have found the crater from the largest explosion the universe has witnessed since its own fiery birth. This is the Ophiuchus supercluster eruption, a blast of such staggering power it carved a void in the fabric of space itself. The discovery began not with a flash of light, but with a ghostly imprint of nothingness. Using a combination of X-ray telescopes and radio observatories, scientists were mapping the Ophiuchus supercluster, a massive gathering of galaxies all embedded within a searing atmosphere of plasma, gas heated to millions of degrees. In the X-ray images which see the glow of this ultra-hot plasma, they expected a relatively smooth, cloudy structure. Instead, they found a staggering absence. On one side of the supercluster's central galaxy, there was a gigantic crescent-shaped edge, and beyond it, a vast cavity where the super-hot plasma was simply missing. It was as if a cosmic bomb had gone off, blowing a hole in the cluster's atmosphere. The scale of this cavity is almost beyond human comprehension. It measures a mind-boggling 1.5 million light-years across. To visualize that, you could line up 15 Milky Way galaxies, each one 100,000 light-years wide, and they would just barely span the diameter of this single, empty bubble. The energy required to create such a void is incomprehensible. Scientists calculate it was equivalent to the simultaneous detonation of several billion supernovae. The source of this cataclysm lies at the very heart of the cavity. In the central galaxy of the supercluster, a supermassive black hole, likely containing the mass of billions of suns, experienced an epoch of unimaginable gluttony. As vast rivers of gas spiraled into its maw, the black hole did not quietly consume everything. Instead, it converted a portion of that infalling matter into two opposing jets of magnetized, ultra-fast particles, blasting them outward at nearly the speed of light. These jets are not gentle streams, they are the universe's most powerful particle accelerators, focused beams of pure energy that can punch through intergalactic space for millions of years. In the Ophiuchus supercluster, one of these jets plowed directly into the surrounding sea of hot plasma. For tens of millions of years, this relentless jet acted like a cosmic blowtorch, relentlessly pushing the multi-million-degree gas aside, heating it further, and inflating this colossal bubble until the black hole's engine finally sputtered and died. Why was this particular eruption so titanic? The answer lies in a perfect and terrifying cosmic alignment. The black hole was likely in a state of extreme feeding, surrounded by a vast reservoir of fuel. The environment around it was also just right, a dense, but not impossibly thick, atmosphere of cluster plasma. This meant the jet could propagate for an extraordinarily long time and distance without being stifled, transferring a truly monstrous amount of energy into its surroundings. It was a black hole operating at the absolute peak of its destructive power for an epoch that dwarfs all of human history. This eruption is not a relic of the distant past. It is a monument to the hidden, cyclical violence that shapes the cosmos. Black holes are not just passive traps for light. They are the most efficient engines in the universe, capable of converting infalling mass into focused, planet-vaporizing energy that can regulate the growth of entire galaxy clusters. The cavity in Ophiuchus shows us that a single black hole can dictate the climate for hundreds of galaxies, preventing gas from cooling and forming new stars across a region millions of light-years wide. It is a breathtaking demonstration of feedback on a supercluster scale, a reminder that the largest structures we see are often defined by the most concentrated points of fury at their hearts. The violence of black holes shapes the universe on staggering scales, but the most profound mysteries are often written in its faintest light. The cosmic microwave background, that ancient afterglow of the Big Bang, is the most perfect thermal radiation we can measure, a nearly uniform sea of cold light bathing the entire cosmos. Yet within this perfect canvas there is a blemish, a region so anomalously cold it has sparked debates that reach beyond the edges of reality itself. This is the CMB cold spot, a vast, circular patch in the constellation Eridanus where the temperature of the primordial light dips far lower than our models can easily explain. Discovered in 2004 by NASA, a Wilkinson microwave anisotropy probe, the cold spot is not just a little chilly. It is a colossal statistical outlier spanning over 1 billion light-years across, where the temperature is about 70 microkelvins colder than the surrounding average. The odds of such a feature arising from random fluctuations in the standard model of cosmology are less than 1 in 200. It is a genuine anomaly, a cosmic sore thumb that demands an explanation. The most straightforward theory points to a vast emptiness in that direction. This idea invokes a phenomenon called the integrated Sachs-Wolf effect. As light from the cosmic microwave background travels through the universe, it climbs in and out of the gravitational wells created by large-scale structures like galaxy clusters and supervoids. Normally, the energy lost climbing out of a well is regained falling into the next. But in an accelerating universe dominated by dark energy, the wells themselves can evolve and shallow as the light passes through. If a photon enters a vast, growing void, it loses energy climbing out of a gravitational well that has become shallower by the time it exits. This net loss of energy manifests as a slight cooling of the microwave background in that direction. In short, a supervoid acts as a hill that flattens as you climb it, leaving you more tired at the top. Astronomers went looking for this proposed supervoid. And indeed, they found one. Surveys revealed a significant underdensity of galaxies in the direction of the cold spot, an immense region hundreds of millions of light-years wide where space is emptier than average. The problem is one of scale. The observed void, while huge, does not seem nearly large or empty enough to account for the profound temperature dip we see. The math simply does not add up. The integrated Sachs-Wolf effect from this known void might explain only about 10% of the observed cooling. This leaves 90% of the mystery chillingly unexplained. So if a void is insufficient, what else could possibly create such a profound cold imprint on the dawn of time? This is where the theories venture into the truly extraordinary. Some cosmologists have proposed a possibility that sounds like science fiction, but is grounded in serious theoretical models. The cold spot could be a cosmic bruise, evidence of a collision with another universe during the epoch of cosmic inflation. In this radical scenario, our observable universe is just one bubble in a frothing multiverse, a vast landscape of eternally inflating space-time where other bubble universes constantly nucleate and expand. If, during our own universe's hyper-rapid inflationary phase, another bubble universe collided with ours, the interaction would have deposited an immense amount of energy at the boundary. This energetic collision would have left a distinct signature on the cosmic microwave background within our bubble specifically, a large circular region with a different temperature profile. Depending on the precise physics of the collision, this signature could manifest as a cold spot, a kind of scar from an encounter with a separate reality. It would be the first empirical hint that our cosmos is not alone, that the totality of existence is far vaster and stranger than we ever dreamed. Of course, this remains a highly speculative idea, one that many scientists view with deep skepticism, favoring more conventional, if still unknown, astrophysical explanations within our single universe. The cold spot, therefore, stands at a crossroads. It is either a puzzling but ultimately explainable feature of our cosmic web, or it is a window into a multiverse, a fingerprint left on the cradle of our reality by something utterly alien. For now, it remains a profound question mark written in the coldest light of creation, a silent, billion-light-year-wide whisper that the universe's greatest secrets may be hidden in its most subtle imperfections. The profound cold spot in the cosmic microwave background is a whisper from the universe's infancy, but a discovery in our own cosmic era has shouted a challenge to one of astronomy's deepest convictions. Drifting quietly in the constellation Cetus are two ghostly galaxies, NGC 1052 DF2 and DF4. These are not brilliant spirals or dense ellipticals. They are ultra-diffuse galaxies, vast, wispy clouds of stars so thinly spread that you can almost see right through them, yet their faint appearance belies a revolutionary secret. Measurements indicate these galaxies contain little to no dark matter at all. This simple finding sent shockwaves through astrophysics because, according to everything we thought we knew, such a galaxy should be impossible. Our entire model of cosmic structure rests on a simple premise. In the early universe, invisible halos of dark matter acted as gravitational seeds. Their immense pull gathered the ordinary hydrogen and helium gas, which then cooled, condensed, and eventually lit up with stars. The dark matter halo is the essential scaffold, the hidden foundation upon which every galaxy is built. Take that scaffold away, and the galaxy should never have formed, or it should fly apart. NGC 1052 DF2 and DF4 defy that logic. They exist as coherent, stable islands of stars, seemingly without the dark matter anchor that every other galaxy requires. The detective work that led to this stunning conclusion is a masterpiece of cosmic forensics. Astronomers led by Pieter van Dokkum used the Dragonfly telephoto array, a unique telescope designed to see extremely faint diffuse light. When they first spotted DF2, its ghostly appearance was intriguing, but the real mystery emerged when they measured its mass. They used two independent methods. First, they studied the motions of the galaxy's own stars. In a typical galaxy, stars orbit at speeds that would fling them into intergalactic space if not held by the gravity of an unseen dark matter halo. In DF2, the stars were moving languidly, their speeds perfectly explained by the gravitational pull of the visible stars alone. No extra dark matter was needed. The second method looked at the galaxy's globular clusters, those dense, spherical swarms of ancient stars that orbit a galaxy like bees around a hive. By measuring the speeds of these clusters, astronomers could again weigh the galaxy. Both methods converged on the same astonishing result. The mass you could see from starlight accounted for virtually all the mass that was there. The dark matter, which should outweigh the visible matter by a factor of 10 to 1, was simply missing. The discovery of a second such galaxy, DF4, confirmed the phenomenon. We were not looking at a fluke or a measurement error. We were looking at a new class of object that breaks the rules. The immediate question was how. How could a galaxy form without dark matter? Or if it did form with dark matter, how could it lose it? One compelling theory looks to their environment. Both galaxies reside near a massive elliptical galaxy, NGC 1052. In the violent past of this group, DF2 and DF4 may have once been normal galaxies with their own dark matter halos. As they swung close to the giant elliptical, its immense gravitational tide could have ripped away not only their stars and gas, but through a complex process, their dark matter as well, leaving behind the ethereal stellar ghosts we see today. Another, even more radical idea suggests these galaxies formed in a completely different way. Perhaps they were born from gas that was violently ejected during a titanic collision between two larger galaxies. This gas, stripped of its dark matter from the outset, could have later pooled and fragmented to form stars, creating a galaxy the wrong way without the dark matter seed. The existence of these galaxies has ignited a fiery debate. Their discovery forces us to ask uncomfortable questions. Is dark matter not as inseparable from galaxies as we believed? Can it be tidally stripped, leaving a galaxy to survive on its own? Or does their formation pathway reveal a hidden diversity in how the universe builds its islands of stars? These faint, almost invisible smudges of light have become one of the most important puzzles in modern astronomy, proving that sometimes the most profound challenges to our understanding come not from the brightest objects but from the quietest ghosts in the sky. The faint ghosts of galaxies like DF2 tell a story of loss, but our own galaxy's halo holds the bones of a conquest. Woven through the ancient stars surrounding the Milky Way is the fossil of a colossal collision, a structure whimsically named the Gaia sausage or sometimes Enceladus. This is not a visible nebula or a stream of light. It is a ghostly imprint in the motions of millions of stars, a pattern of orbits so distinct it reveals a cataclysm that forged the Milky Way as we know it. The discovery was made possible by the European Space Agency's Gaia spacecraft, an observatory on a singular mission to chart the positions, distances, and motions of over 1 billion stars with breathtaking precision. As scientists began to analyze Gaia's first massive data releases, they noticed something extraordinary in the motions of stars within our galaxy's halo, the sparse, spherical cloud of ancient stars surrounding the main disk. A huge population of these stars was not moving in random directions. Instead, their orbits were highly elongated and radial, like needles pointing directly toward and away from the galactic center. When plotted in a graph of orbital characteristics, this dense clustering formed a distinct sausage-shaped blob, giving the structure its memorable name. These stars were the tracers, the surviving population of a dwarf galaxy that met its end 10 billion years ago. This was no minor merger. The Gaia sausage represents the remains of a galaxy perhaps 1/5 the mass of the young Milky Way itself, a titan by dwarf galaxy standards. Astronomers have named it the Enceladus galaxy after a giant of Greek mythology to reflect its substantial size. The collision was not a glancing blow. It was a head-on catastrophic merger. The smaller galaxy plunged directly into the heart of the proto-Milky Way. In the violent chaos that followed, the dwarf galaxy was completely torn apart by tidal forces over hundreds of millions of years. Its stars were scattered, but they did not adopt random orbits. The physics of such a direct radial collision funneled them into those characteristic elongated paths, plunging deep into the galactic center on steep trajectories before swinging far out into the halo again. These stars are the archaeological evidence, the celestial DNA that allows us to reconstruct this ancient event. By studying their chemical composition, which differs from native Milky Way stars, astronomers can even begin to understand what the lost galaxy was like. It was old and metal-poor, suggesting it formed its stars early and quickly before the merger ended its independent existence. The impact of this merger was nothing short of transformative. It did not just add a swarm of stars to the halo, it fundamentally reshaped the architecture of the young Milky Way. The immense energy of the collision is thought to have violently puffed up the galaxy's primordial thin disk of stars and gas, scattering material to much greater heights above and below the galactic plane. This event likely gave birth to the Milky Way's thick disk, that distinct component populated by older stars that orbits in a more spread-out, fluffy layer. Furthermore, the influx of stars and gas from the doomed dwarf galaxy, funneled directly into the galactic center by those radial orbits, may have contributed significantly to building the Milky Way's central bulge, that dense, spherical hub of stars at its heart. In essence, the Gaia sausage merger was a defining act of violence that crafted two of our galaxy's major components. It is a stunning example of galactic archaeology, where the subtle motions of stars today allow us to read a dramatic chapter from 10 billion years in the past. This discovery reveals that our seemingly stable spiral galaxy is in part the product of a gargantuan act of cannibalism, a foundational trauma written in the orbits of ancient suns. This ancient merger shaped our galaxy's foundations, but the local architecture of star birth holds a surprise of its own. Winding through the very heart of our galactic neighborhood is a structure so immense and graceful it redefines our map of nearby space. This is the Radcliffe Wave, a colossal, undulating ribbon of stellar nurseries and young stars, a continuous wave-shaped chain nearly 9,000 light-years long. For centuries, astronomers have catalogued the bright nebulae and star clusters of our local spiral arm as separate entities. The Orion Nebula, the Taurus molecular cloud, the star clusters of Perseus, these were seen as distinct landmarks in the cosmic geography of our galactic suburb. But in 2020, a team of researchers led by astronomers at Harvard University made a stunning connection. By using precise distance measurements from the European Space Agency's Gaia mission, they constructed an accurate three-dimensional map of these star-forming regions. What emerged was not a scattered collection of clouds. Instead, the data revealed a single, coherent sinusoidal structure, a gentle S-curve that snakes above and below the galactic plane like a cosmic roller coaster track. This wave is the largest gaseous structure ever identified within our own galaxy, and it is literally the backbone of local star formation. Its crests and troughs are not empty space. They are dense concentrations of molecular gas and dust, the very raw material for new solar systems. At its peaks, the wave rises nearly 500 light-years above the galactic midplane, and at its dips it sinks a similar distance below. Riding along this immense undulation are most of the famous stellar nurseries we know, all connected in a single, flowing river of potential. The very existence of this wave presents a beautiful and immediate puzzle. What is it, and why does it have this perfect wave-like shape? The first and most intriguing possibility is that we are witnessing a true wave oscillation in the disk of the Milky Way itself. Imagine the galactic plane as a vast, tranquil pond. If a massive object like a dwarf galaxy or a large dark matter clump passed through this pond billions of years ago, it could have set off a gravitational ripple. This ripple would propagate through the disk, causing the gas to rise and fall in a coherent pattern that persists to this day. In this model, the Radcliffe wave is a fossilized vibration, a slow-motion undulation frozen in time, with star formation happening most vigorously at the peaks and troughs where the gas is most densely compressed. A second theory looks to a more violent origin. Perhaps this wave is the scar from a direct hit. A small, gas-rich satellite galaxy might have collided with the Milky Way's disk in the relatively recent past. As it plunged through, its gravitational disturbance would have kicked up a wave of gas in its wake, much like a speedboat creates a lasting wake on a calm lake. The structure we see could be that wake, now settling back down and forming stars along its length. Then there is a third, more structural idea. Could the Radcliffe wave be a local segment of a spiral arm, a spur that is itself warped and twisted? Our galaxy's spiral arms are not perfectly flat. They can exhibit vertical wrinkles and corrugations. This wave might be one such wrinkle, a kink in the local arm where star formation has become focused, making its three-dimensional shape dramatically visible for the first time. The discovery forces a profound shift in perspective. We no longer live in a region of isolated stellar nurseries. We live along the slope of a single, gargantuan wave of creation, a wave so large it takes light 9,000 years to travel from one end to the other. Our own sun may have been born in a similar structure eons ago. This finding shows that star formation is organized on a scale far grander than we ever imagined, even in our own cosmic backyard. The local universe is not a random scatter of clouds, it is a symphony, and the Radcliffe wave is one of its deepest, most resonant notes, a fundamental rhythm in the process of building stars and planets right next door. From perfect rings to titanic walls, from invisible halos to ancient streams, the universe's architecture defies simple explanation. Each of these 25 puzzling structures is more than a cosmic curiosity. It is a direct challenge to our understanding of physics itself. They force us to question the rules of gravity, the nature of dark matter, the limits of cosmic expansion, and even the very shape of reality. A galaxy without dark matter should not exist, yet we have found it. A wall of galaxies 10 billion light-years long should be impossible, yet its outline haunts our maps. A cold spot in the primordial glow might be a bruise from a collision with another universe. These are not minor puzzles, they are fundamental cracks in our cosmic picture, each one an invitation to rethink everything we thought we knew. the journey does not end here. With new eyes on the cosmos like the James Webb Space Telescope and the Vera Rubin Observatory coming fully online, we stand at the threshold of a new era of discovery. These instruments will peer deeper into the early universe, map the cosmic web in unprecedented detail, and undoubtedly reveal structures even more bewildering than those we have just explored. Some of today's greatest mysteries will be solved, only to be replaced by new, even more profound questions. So the next time you look up at the night sky, remember that the quiet darkness is not empty. It is filled with invisible walls, ghostly streams, and colossal rings, a hidden architecture of wonders waiting to be understood. Which of these galactic enigmas left you the most awestruck? Share your thoughts in the comments below.